Again, this warm-up that you had is reviewing what we did before break. And our new unit that we're working on is called relationships within a triangle. So we've taken two triangles and compared them to see if they're similar. We've compared them to see if they're congruent. What we're doing now is just looking at one single triangle and the relationships within it. And so some of that vocab that you did will be addressing today about particular properties within that triangle. So before break, we learned whether or not it is a triangle, if it's acute, obtuse, or right, how to check each of those, how to order the sides or the angles in order for the least to greatest or vice versa. We also dealt with diagram there. We did some factoring. We did a lot of little stuff like that for you. So this warm-up is going back through some of that stuff we did to kind of refresh our memories before we get going today. You with me, Faisal? Yeah. Good. All right, so for number one, we're talking about ordering the sides and ordering the angles based upon the information given to you. So this first example, what is the largest angle? What was our answer for this? Angle B. How did I know that angle B was my largest angle? Opposite of the largest side. So AC is the longest side, which means angle B must be the largest angle. Okay, all right. So in here it asks us to list the angles from smallest to largest. What was my smallest angle? Okay, good. Because again, it's opposite of the smallest side. All right, my medium angle? Angle L. And then my largest angle? Angle J. Okay. Any questions on those two? All right. So then here, list the order of the sides from smallest to largest. What was my actually, first we need to know our third angle. What was this angle J?
45.
45, do we agree with that? We're all good with that? Okay. So what was my smallest side? JL, are we good with that? Okay. And then what's my medium side?
LK.
LK. And that leaves my largest as? JK. Now I want you to pause and take a look at your paper. Do you have proper notation of the segments over time? We're listing the segments, not talking about the measures of the segments. We're just listing those sides. We need to use that segment notation. Alright, questions on that? Two. Okay, so then our next piece is determine if a triangle can be made with these three sides. How do I know if a triangle can be made given any three segments?
The sum of two of the sides has to be bigger than the other side.
Good. So my small and my medium must be bigger than the large. So this is our shortcut because it's any two must be bigger than the third, but we came to understand last year, that we only need to check that the small and medium add up to be bigger than large. Alright, so for A here, my two small sides are 3 and 7. And we're comparing that to side length 8. And indeed, 10 is bigger than 8, so yes, this creates a triangle. What do we get for B?
No.
And how about C?
No.
Okay. Questions on that? Alright. So now on the back side, it talks about how to find the range of our third side of a triangle. So they give us two, and we have to find the possible lengths, the range of lengths, where that third side could be. Now, again, we did it at first a long way, but then we realized a shortcut. What is my shortcut? How do I determine my lower value, my upper value? Teresa?
You take the bigger number and subtract the smaller number to get the first number.
Good. So we have 6 minus 4 is 2, so subtract them.
And then you add them to get the bigger thing.
Good. And 6 and 4 is 10. So again, we want to subtract them for the smaller value and add them for the larger value. So our next one says, can 8 be a third side of a triangle given the other two sides are 10 and 15? Yes or no?
Yes.
Yeah. If we look at the range, 10 and 15 subtracted would be 5, added together is 25. This falls within that range, so it can be a third side. But can 25 be a third side?
No.
No. It does not equal 25. It has to be less than 25. Alright, questions on those ones? Okay. And I realized during first period that this was lacking another key thing that we learned last time. So if you would just copy this down off to the side. Just a reminder of how we can determine if it's a right, acute, or obtuse triangle. So I'm comparing my side squared, where c squared in a right triangle is that hypotenuse. Okay, so if my a squared plus b squared equals a c squared, what type of triangle does this create? Right triangle. Now, if my c squared is larger, what does that create? Obtuse. Good. And if c squared is smaller, that leaves me with an acute triangle. And again, c is going to be that longest side. Alright, so don't forget those. Okay, and then last, we have probably the trickiest part of what we learned before break. So it's identify the smallest segment in each diagram. And what we have are two triangles sharing a side. So we have to find of all 5 side lengths, which one is the smallest. Zoom in on this. Alright, so I'm going to go ahead and have you guys help me out in filling in our remaining angles. What was angle BDA?
65.
65. 65? Give me thumbs up if you agree with that. Okay, so make sure there's a majority. And what was angle C?
37.
Okay. So now let's go ahead and take a look, starting with just my left triangle here. What is my small side of this triangle? BD. What's my medium side?
AB.
Leaving AB as my large. Are we good with that?
Yes. Yeah.
So now I'm going to take a look at the triangle on the right side. What is my small length on this one? That guy? Is that what you guys said?
Yeah.
Okay. And what's my medium?
BD.
BD. And this is my large. Alright, so what we need to do is compare our two small lengths to figure out which one is smallest. It's easiest for us to go ahead and take a look at the triangle that contains both of these. So that was the small of my red triangle, and this is the small of the green triangle. And the triangle that contains both is going to be this triangle here. That allows me to compare them to one another to know which one is smallest overall. So when I take a look at that blue triangle, which one is smaller, BD or DC? And why DC?
Because BD is the medium one.
Right, within this triangle, BD is my medium one. If I look, angle C, which is the angle across from it, is larger, 37 degrees, than angle DBC, because that's only 36 degrees. So I can know then that the smaller angle is going to yield the smaller angle. So my answer is side DC. And again, make sure you have that proper notation. Alright, questions with that one?
Why can't you just, why is that one, is the next one doesn't share the same triangle?
You mean, are you talking about this picture here?
But can you just, I don't know.
Are you sure?
Yeah.
Okay. Yes, something?
Well, isn't BD 28? Is it 28?
It is 28 degrees, but we talked about this before break, so I could have a triangle like this. Let's just say that this is 30 degrees. And I could have the same angle. But I didn't do a very good job. Let me use that same triangle. I could have the same angle, but depending on what those other angle measures are, notice that these are different side lengths. So even though this angle is smaller, within this triangle, all that tells me is that BD is the smallest side of this triangle. I don't know that's the small side of the whole thing, because it only tells me my relationships within a triangle, not within, like this would be what, quadrilateral. It only lets me know the relationships within one triangle. So to know then between these two small sides, which one is smallest overall, I need to compare them to each other, and so they need to be in the same triangle to compare them to one another. So this was the smallest, BD was the smallest of the red triangle. and DC was the smallest of the green triangle. So comparing them to one another, I can see that BD is across the 37-degree angle, and DC is across from the 36-degree angle. The smaller angle of those two is going to yield the smaller side. So it's not just the smallest angle of the whole picture, but the smallest angle within that triangle, and then you do you have a question? Okay. Other questions with that one? Okay, so then what did we get for our answer over here? Ooh, ZY or WX. Let's take a look. What did we get for this angle?
65.
Alright, and then what did we get for... Oh, these are two isosceles triangles. What fun! Okay. So in my top triangle here, would you agree that the smallest one is WX?
Yes.
And then these are the same. I'm just going to call them both U's. Wait, what? It's isosceles. Oh, you're right. You can call them both larges. Call them both extra larges if you want. Alright, and then over here, my smallest sides, well, I have two side lengths that are the same, right? So that would be small, that would be small. Do we agree with that?
Yeah.
And then 120 is going to be my large or my medium. I'm going to call it my large. Okay, so now I need to compare. Now, since these are the same lengths, I want to go ahead and use the triangle that has... I want to go ahead and use the triangle that compares both smalls. So this is my small and my top triangle. Now both of these are smalls of the bottom triangle. I'm going to go ahead and use this one. They're the same side lengths. So since this one is contained within that same triangle, then I'm going to choose to use that one to compare. So looking at this, between these two, even though this was the smallest of the blue triangle, there's one even smaller than that in my green triangle here. So WX is the smallest overall, because again, this is smaller than that side based upon that relationship there. So WX is going to be my overall smallest side. Questions on that one? Again, probably the weirdest part of what we learned before. Okay. Go ahead and set that aside. That was, again, just to kind of refresh memories of what we did. Let's take a look at our vocab. Alright, so you guys went through and filled in the vocab from the textbook. So let's go ahead and talk through what we've learned with this and kind of draw pictures to help us visualize what's going on. Today we'll be focusing on perpendicular bisector and angle bisector, but we will learn all this before the meeting. Alright, so the first thing, I went ahead and defined a couple of things up here for you. So concurrent lines is when we have lines that meet in one point, three or more lines that meet in one point. And the point at which they meet is called your point of concurrency. So I can have all three lines meet at one point. And that is my point of concurrency. Okay, so where they all meet. Now notice all three have to meet at one point. So if I had something like this, all three do not meet at one single point, so these three lines are not concurrent. Okay, so all three need to meet at one single point. The other thing that I put on here, this is something we actually discussed, I think, the first or second day of school. But when we talk about the distance from a point to a line, so if I were to draw a line and a point off of it, if I were to talk about the distance from this point to the line, we are always going the shortest distance, which is it's the perpendicular distance. So if you were to draw straight down to it, whatever that perpendicular distance is, that's going to be the shortest distance. That's what we're talking about. When we talked about this at the beginning of the year, I said if I were to walk from here to the wall, I would go the shortest distance straight back to it. I wouldn't come over here. I wouldn't weave through. I'd go straight to it, which is always that perpendicular line. So again, I'm not going from that point over here, I'm not going from that point down there, I'm going the shortest distance, which is always going to be straight down to it perpendicular. Alright, questions on those two before we dive into the bulk of the vocab? Get ready to draw some triangles. So perpendicular bisector and angle bisector. Now we have dealt with these terms throughout the year, but we're going to be looking at it specifically, their relationship within a triangle. So we know perpendicular bisector looks like, and I'm going to have us actually go and draw what it would look like in a triangle. So perpendicular bisector is a line segment or ray that is perpendicular to the segment at its midpoint. So let's go ahead and draw a triangle, whatever kind of triangle you want. And I'm going to draw a perpendicular bisector. Actually, I'm going to... Nope, I want that back. I'm going to draw a perpendicular bisector through this bottom line here. So it goes through its midpoint. So on your picture, go ahead and give the approximate midpoint. And midpoint means it's cut in half. And it's a line segment array that is perpendicular at that midpoint. So go ahead and do your best to draw a line perpendicular through there. And go ahead and put in that notation so you know that it is to be perpendicular. Alright, so this is a perpendicular bisector. I did it just to one side of my triangle. I can cover up that's going on. You can see it cut it in half, and at its midpoint it's perpendicular. Notice my perpendicular bisector does not have to go through that angle opposite. It might, but it's not a requirement. Its only job is to guarantee that it goes through the midpoint and that it's perpendicular. How many perpendicular bisectors could I draw within a triangle? Turn top to your shoulder part real quick. How many total could I draw?
How many could we do?
Alright, tell me on your fingers how many I can draw in one triangle. I see only about 2/3 of the class holding up fingers. 3, good. We only have 3 sides, right? We only have 3 segments to bisect. So I only have 3 possibilities. Now, I'm just going to do a rough sketch. You don't need to draw it, just keep the one. I can draw a rough sketch of them. And we're going to be learning next class a key characteristic about our perpendicular bisectors within a triangle. So I can draw 3 of them because there are 3 segments that can be bisected. Alright, next up, angle bisector. Yes? That was me quickly trying to demonstrate it going through the midpoint and perpendicular. Next class we'll have nice figures. Yeah, so it's perpendicular bisector must go through midpoint and must be perpendicular. Only requirements. Alright, so next, angle bisector. Again, we know what an angle bisector is. It's an angle that gets cut in half. Or it's what cuts the angle in half. But let's take a look at this again within a triangle. So draw whatever triangle you want. So it says a ray that divides an angle into congruent angles. I'm going to go ahead and bisect this top angle here. So do your best on your picture to draw it bisected. Looks decent. Alright, and go ahead and draw on the markings to indicate that those are congruent. Now, once again, notice the angle bisector doesn't necessarily have to go through the midpoint. It doesn't look like it does on my picture. It's not required to. Its only requirement is that it cuts the angle in half. Alright, questions on perpendicular bisector or angle bisector? So next up we have new stuff, medians and altitudes. Alright, median of a triangle. A segment that has as its endpoints a vertex of the triangle and the midpoint of the opposite side. So it's a segment where one endpoint is the vertex and the other endpoint is the midpoint. So once again, let's draw a triangle. And I'm going to go ahead and use this top one as my vertex. So side opposite would be this bottom side. approximately drawing your midpoint. Again, I'm just eyeballing it here. And it's the segment that connects those. So let's go ahead and put in some markings. It connects the midpoint in the vertex, so guaranteed this is cut in half because this point here is the midpoint. Is my angle necessarily bisected? No, it could be, but it does not have to be. It is only required that it connects the vertex and that midpoint. So it must cut it in half. It does not have to cut the angle in half. Does it have to be perpendicular? No, it's not required to. It might in certain triangles, but it is not required to. It's only required to connect the vertex and that midpoint. All right. How many medians can I draw in a triangle? 3. How many angle bisectors can I draw in a triangle? 3, because there's only 3 angles. All right. Next we have altitude. So it's the perpendicular segment from a vertex to the line containing the side opposite that vertex. What happened? Once again, let's draw a triangle, whatever triangle you want. All right, so we see it has to be perpendicular. And it has to go from a vertex to the side opposite. I'm going to go ahead once again use this top vertex as my starting point. So side opposite would be this bottom one, and it must hit it perpendicularly. So do your best to draw it perpendicular and draw on that marking. I feel like altitudes are the hardest to draw, in my opinion, because it's hard to nail that perpendicular. Now, in altitude, there's nothing said about the angle. The angle does not have to be cut in half. In my opinion, it does not have to be. It does not say anything about hitting at its midpoint. It might, but it does not have to. Its only requirement is that it goes from the vertex to the opposite side at a perpendicular marking. Now, sometimes our altitudes actually fall outside of the triangle. So, for example, and you don't have to draw this down, this is something we'll investigate in a couple of days. But if I had an obtuse triangle, and I wanted to do, let's say, the altitude from this vertex. Well, if I go to anywhere over here, none of those are going to be perpendicular. In fact, it hits perpendicular outside of the triangle. And so what we end up having to do is extend that side out in order to draw in that perpendicular mark. Which is why it says to the line containing the side opposite, because sometimes the perpendicular or the altitude doesn't actually hit the side, but it hits the extension of it. So we do have sometimes our altitudes lie outside. The rest of them, though, cannot lie outside of it. All right. Questions on medians or altitudes? And how many altitudes can I draw in a triangle? 3, because again, it's going from the vertex to the side opposite. Okay, and last but not least, the mid-segment, which we actually already dealt with before. So mid-segment is the segment that joins the midpoints of the two sides of the triangle. So draw whatever triangle you want.
Sorry, I asked for your picture at that one instead of.
Can you fix it, or did you do it in 10?
I didn't. It's okay. I'll just draw it.
Okay. All right. So mid-segment of triangle, it joins the midpoints of two sides. So you get to pick which two sides. I'm going to go ahead and pick this side. Let's see. That's about the midpoint. And this side, maybe about there. So that is my mid-segment. Now, how many mid-segments of a triangle can I draw? Talk this one over with your shoulder partner. Feel free to do a little doodle on your paper.
One makes the other
Alright, don't bring it back up front. Show me on your stand how many fingers of how many times can I do mid-segments. I see 1, 2, and 3. let's take a look. So it joins the midpoints of two sides of a triangle. So I have done the left and right side. How about I do the right and the bottom? Okay. There's another midsegment, and then bottom and the left. Huh.
That's the drawing that we saw.
Yes, you have seen that drawing before.
Skip it.
I don't.
So we can have three midsegments in a triangle as well. Alright. Questions with that?
So what?
So, quite a bit of new vocab, but really the newest things was just median and altitude. The other stuff we had first. Alright, so next what we're going to do is learn about the perpendicular bisector theorem and angle bisector theorem. So you can set this vocab away. We will come back to it in future classes. So don't lose it until we're done with it. I'm sorry, you're still stuck fast. Okay.
Yeah, just call it down.
Great, so again, today we're focusing on perpendicular and angle bisectors. So today we're not going to be focusing on it within a triangle, just information about it in general. Next class, we're going to take a look at what characteristics they have within the triangle. So today we are going to continue with constructions. We have done these constructions before, but it was a while ago. So we're going to recap, refresh, for some of you, learn how to do these constructions, which requires us to get compass and ruler. So this half of the classroom, get a compass. This half. Get a ruler and then swap.
I'll give you back the one.
I'll give you a ruler.
Alright, so make sure you're on the side that says perpendicular bisector theorem. That's what we'll be starting off with. Alright, so perpendicular bisector theorem. The point is on the perpendicular bisector. If a point is on the perpendicular bisector of a segment, then it is equidistant. Yeah, what does equidistant mean? Equal distance. It's the same distance.
Why shouldn't it just say equal distance?
You'll see when I finish the sentence. Grammatically, it would say. Alright, so if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. From the endpoints of the segment. So we're going to start off by drawing just a rough sketch to represent this, and then later we'll actually construct a perpendicular bisector and investigate. So let's start off by drawing just a little segment. And again, you can freehand this. We won't go too crazy with the segment AB. And do your best to draw the approximate perpendicular bisector. Remember, it should meet at its midpoint. And be perpendicular to that. Alright, so this is our starting point. we have a segment with its perpendicular bisector. Now what this theorem says that if a point is anywhere on that perpendicular bisector, then it should be the same distance away from the endpoints. So go ahead and pick where you want to put your points. You can go above, you can go below, you can go super high above, very close to it. Either way is fine. I'm just going to stick it right above. Call that point C. According to this theorem, as long as it lies on that perpendicular bisector, then that distance from C to the endpoints is going to be the same. Right, so it can be anywhere along here, but wherever you put it, it will be the same distance away from the endpoints. Now let's talk about why this is true. So we just filled in what the theorem says that that distance will be the same. But how can we know that's true? So let's take a look at what our starting information is. Our starting information is that we have this perpendicular, and it's bisected so that those two pieces are the same. If I were to ask you to prove this, how could we go about showing that these two segments are indeed congruent? Talk with your shoulder partner. How can I show that AC and CB are congruent?
If those equal, and that's why we notice that.
Oh, that's bad. Sorry, starting.
Alright, so bring it back up front. Now I heard some stuff about triangles. So I see we have two triangles here, very good. And I heard some side angle side, is that what you guys were saying? If we did not say side angle side, what did we say? HL, hypotenuse slave. Okay, what other options? Anything else we want to investigate? Alright, so let's investigate side angle side and HL. So HL is hypotenuse slave. Right now, do I have its right triangle? Yep. Do I have the hypotenuse? No. Double A? Yeah, so I only have one of the pieces. So unfortunately, we can't use HL because we don't have the hypotenuse. That's what we're trying to show. So unfortunately, HL won't work. Let's try side angle side. Do I have a set of sides?
Yeah.
Do I have a set of angles?
Yeah.
Do I have another set of sides?
Yeah.
Where? Yep, C to our midpoint here. So perhaps, let me call that X. Okay. So how do I know that that is congruent?
It's the same line.
It's the same line. Reflects, a very good thing. So now I have side angle side. We know that this is also going to be a right angle. So I can say then that triangle CAX is congruent to triangle CBX by side angle side. So that tells me the triangles are congruent. But what lets me then say that CA is congruent to CB? How do I know that? CPCTC. CPCTC. And then I could say from there that CA is equal to CB. What would be my reasoning for that? It's been a while since we've used that one. I heard it amidst people over here. Definition of congruent segments. Good. So we could actually prove this theorem to be true. That's how we know that it is true. All right. So I'm going to go ahead and put my markings back in here. Okay, so that's what our perpendicular bisector theorem says. Any point along our perpendicular bisector is equal to 6 on the endpoints. Now, if you would please put a little asterisk here and write in converse is also true. So the converse of of the perpendicular bisector theorem is also true. And that would be, remember, we go backward. So the converse says that if there is a point equidistant from the ends, then that means that point lies on the perpendicular bisector. So it goes both ways. And either way, we'll just call it perpendicular bisector theorem. Okay, questions with that?
Because it's a perpendicular bisector, so you know A and X and X are equal.
Yeah. So we know perpendicular bisector then would give us by definition those. Other, excuse me, questions? All right. Excuse me. Let's go first to the backside. Let's talk about our angle bisector theorem. Then we'll come back and draw them with our compasses. So angle bisector theorem is going to sound pretty similar. Just a little different. All right, if a point is on the bisector of an angle, it is nice to have an angle. If a point is on the bisector of an angle, then the point is equidistant so it starts to sound the same so far, and the end's just a little different. And the point is equidistant from the sides of the angle. So if the point is on the bisector of an angle, then the point is equidistant from the side of the angle. Ooh, let's see if we can think through this one. Why doesn't it say it's equidistant from the endpoints of the angle? Why aren't there endpoints of an angle? They're rays, yeah. So for an angle, we don't have endpoints because they're rays. They go on forever. All right, so go ahead and draw whatever type of angle you want. Obtuse, frank, whatever you feel like. And I'm going to call this ABC. And again, A and C are just simply there to help me label my rays as ray B, A, and ray B, C. And do your best to go and draw on the angle bisector. And indicate that is so with little markings. Alright, so what our theorem says is, again, we're starting off with an angle bisector. And it says if a point is anywhere on that angle bisector, so slap one on there, I'm going to throw one there. I'm going to call it X. Then that point is equidistant from the sides. And this goes back to that very first chunk of our vocabulary that says the distance from a point to a line is always that shortest distance or that perpendicular distance. So do your best to draw in the shortest perpendicular. And I know it's not going to be perfect. And so what our theorem tells us is that those will be the same distance. So again, equidistant from the sides, we're going from a point to a line, so we go with the shortest distance, which is that perpendicular distance. Now, again, we can prove this guy to be true as well. So let me pull off the markings that we threw in. This is what we start off with our theorem. We have an angle bisector, a point on the angle bisector, and we're looking at the distance directly from it. Talk with your shoulder partner, how can I prove that those two segments are the same? I'm going to go and label these. That what? The x, y, and x, z are concurrent.
You can say angle side.
But then that
Yeah, you have angle.
wild cherry.
You have
I
angle.
like lemonade. I'm a fan of the mountain cooler or splash. I haven't tried that. Alright. So it comes back to triangles again, right? Is there any additional information I know about my picture before we try saying something about the triangles? Nothing? Bx? What about Bx? Good. It's congruent to itself, right? Because of reflex property. So how can I show that those two triangles are congruent? Angle, angle, side. Any other options?
Side angle, angle.
Side, angle, angle. So same thing, just reversal.
Yeah.
Anyone try HL? Can I do HL with this?
Yeah.
No.
You don't know?
Yes.
Those that are saying no, what am I missing?
No leg.
A leg. I have a hypotenuse. I have the right triangle, but I don't have a leg. So my only option is angle, angle, side. Angle, angle, side. Alright, so I can say that a triangle, let's go with XYD, is congruent to triangle XZB by angle, angle, side. Again, we had that reflexive property before there. So then I can say that segment XY is congruent to segment XZ by CPCTC, which means that the measures are yeah. Alright, I'm gonna go put my markings down. Alright, so in both of these cases, this is the takeaway. What our theorem tells us is that that distance is the same. And likewise over here, this is our takeaway. Our theorem tells us that this distance is the same. Okay. So, interestingly, both these were using great triangles. Come on.
For angle bisector theorem, is it optical theorem?
Yes, yeah, the converse is also true for this one. Converse is also true. Thank you. Alright, other questions?
The right angles, did you get those because like how your angle was shaped, or is it like?
So we got this because it's talking about the point from the distance from the sides of the angle to the point. And whenever we go from a point to a line, it's always going to be the perpendicular distance that we're talking about. Other questions of these two? Okay, let's bust out the compasses and go back to perpendicular bisectors.
Thank you. Yeah, let's go with that. Which one is? I'm looking for a C and C. So you want to go around the other. Yeah, that's
So hard.
Alright, so perpendicular bisectors. Now we did perpendicular bisectors before. And bear with me because it's a lot easier to do it by hand than it is on the smartboard. So you may go faster than me, that's fine. So it says to start off by drawing a line segment AB. So you get to pick where you want it, how large or how small. Keep in mind we want it to fit on the paper. I'm just going to label this segment AB. Now some key things about your compasses. Remember, the larger the construction, the more accurate, but bear in mind it needs to fit on the paper. As well as you want to make your line as fine as you can, because you want to be as exact as you can with your compass to fit on the endpoints. So for example, last class when I started out, I did a big dot on it, and then I lost track of where the exact center was. So I'm leaving it with just the endpoints there. Okay. So then it says construct the perpendicular bisector of AB. And if you forgot how to do it, we'll do it together, as well as it gives you a reminder here in the parentheses. So set your compass for more than half the distance. I'm just checking that it's more than half. That looks good. And draw intersecting arcs from both endpoints. So once you've chosen the distance for your compass, we're going to keep that the same. So tighten it real good. And we're going to draw intersecting arcs above and below. You don't need to do the whole arc. You can just do little ones. So is it going to work for me? So above and below. And again, you're going to keep that distance the same on your compass. And do the same thing to the other side. Bless you. And if you have to go back, okay, don't mess up on me. And if you have to go back because you didn't quite get the arcs to intersect, that's fine. Just keep that distance the same and you can redraw. So, I just set those up. Alright, so again, your compass stays at same distance on both sides. Now these two intersections, that's what you're connecting with your ruler. Okay, so go ahead and do that. I'm just going to come around. Raise your hand if you need help. We'll cover those that need assistance while you guys draw them. And go ahead and connect those. Draw that line.
Oh, I didn't see this right.
And go ahead and put in the markings that it's perpendicular and that it cut that segment in half. Yeah, so go ahead and connect those intersections. Alright, you guys all look good, so I'm going to catch up. And again, go ahead and just mark that it's perpendicular, that those are. Alright, so we're just going to investigate this theorem. We know that according to the theorem, any point along here should be the same distance from the endpoints. And so we're going to go ahead and check that out. Now keep in mind there is going to be, it might be a little off, just due to human error because we're not getting it exact. So we should get pretty close to the same distance. So that's what this next part is saying. What we've done here is construct a perpendicular bisector. This is one of our big constructions that we do in geometry. It's one that will be on the S12. So this, we just did, you need to know for the future. Now this next piece, this is just us investigating it. Alright, choose a point on the perpendicular bisector and label it C. You can choose whether you want above or below, how close or how far away you want it to be. I'm going to go below. Call that C. And then go ahead and use your ruler to draw in segment AC and draw in segment CB. And again, you can place your point C wherever you want. And once you've drawn those segments, go ahead and measure them to see if you got it. See how close you got with it. I don't care if you use centimeters, millimeters, inches, whatever you prefer. And as you get those, go ahead and write what those measures are, just to see how close you got. Once you've got it, go ahead and show it off to your shorter partner, show them how well you did. And take note that your shoulder partners might be a different distance than yours, which is perfectly fine, because we're all drawing different scenarios. But the idea is that whatever you got should be the same within your process.
Not too bad.
Okay, go ahead and show me your papers so I can see how we did. Wait. Nice. You guys are doing awesome with this. Okay. Let's go ahead and squeeze out just drawing the angle bisector on the other side, and the next class we'll come back together and finish it out. So flip it over. Angle bisector. Again, you can go and draw your angle ABC however you want. Acute, obtuse, right? Whatever style you like. I'm going to go with an obtuse one. Nope. Alright, so you get to draw whatever type of angle you want, and then we're just going to go ahead and bisect angle and pause our construction of that. Alright, so to bisect our angle, you get to pick the distance on your compass, but you want it to intersect both sides. So just make sure that it will intersect both rays. Alright. So just mark the little marking where it intersects on both sides. You don't have to draw the whole arc. You can if you want to, but it's not necessary. And then you can either leave your compass the same or make it a little bit larger. You're now going to set your compass on those markings, on those intersections, and draw a little arc on either side to intersect there. Okay, so again, you can leave your compass the same or adjust it and draw those intersecting arcs there. That is what you're going to connect for your angle bisector. Hope you guys are having an easier time than I am right now. What? And then we will continue with that piece. Alright, I'm going to go ahead and pass out your homework to you. Your homework is worksheet 1. While I do that, go ahead and return the rulers and the compasses. Notice on worksheet 1, it tells you to stop at number 29.